Okay.
Right.
Can I stop?
Is it? Okay. So the next speaker is Xinlian Liu from University of Tokyo.
Okay, I think I can start. And today I'm going to tell you our attempt to find a systematically improvable 3D real space RG. And at this point, we haven't achieved this goal, but we have found a real space RG transformation with well-controlled approximation errors. And today I'm going to tell you the detail of this quest. So we have been thinking about universality since the beginning of theoretical physics. And the universal gravity gave us one of the three constants of nature, and also inspired Einstein to propose his general relativity. And for a gas system in a low temperature limit, the behavior of many different gases follow a universal law. This is the ideal gas law, and this gives us one definition of an empirical temperature scale. And if you study the liquid-gas phase transition, and at this critical point, the critical pressure and volume depends actually on different gas molecules. But how these kind of values approach its critical value, its behavior is universal and characterized by these exponents. And one very powerful way to predict these exponents is using RG method. And you do some coarse graining, and this will generate an RG flow in the coupling constant space. And the behavior of the flow near a critical fixed point tells you about these exponents. So the prototype of almost all real space RG transformation is Kardanov's block spin idea. You take a block of spin and you replace it by a causal spin, and by doing this, you will generate a flow in the coupling constant space. In 1975, Wilson implemented a numerical way to do this using a 3x3 block spin map by keeping around 200 couplings of a 2D Ising model, and the result is pretty accurate. The error is only 1% or even 0.1% for the first two exponents. However, at the end of the analysis, Wilson comments that this method is difficult for 3D Ising, since a similar block spin configuration will contains kind of 10 raised to nice power of configuration, which is computationally impractical. And the next year, Migdal and Kardanov proposed the bound moving trick, which is easy to implement, but the numerical error is very large. It's almost about 50% due to the fact that in this approximation, the error is kind of uncontrolled, and you have any systematic way to including more and more couplings. And the way to improvement Kardanov's idea is using this tensor network reformalization. And the key is to focus on the spins at the boundary, and you sum over all the spin in the bulk. And then the partition function of this subsystem can be represented by a tensor with 4 legs. And by putting different tensors together and connecting their legs, you can reconstruct the partition function of a larger system. And for a 2D classical system, this reformalization gives you a different perspective of understanding 2D RG using tools from like 1D quantum chain, which is mentioned in the first talk. So we can use the idea called the entanglement entropy area law to tell us how large is the RG error and what's the behavior of the RG in the coupling constant in this tensor space. And this is due to Levin and Nave in 2007. And this area law tells us in 2D or 1+1D, as the system size becomes large, the entropy tends to saturate. And this constant entropy can give us a justification of the common numerical practice of only keeping a constant number of couplings when you do the RG transformation. And the other nice thing about this reformulation is that when you implement a real space RG by manipulating this tensor using singular value decomposition, you do some truncation, and the truncation error quite naturally give you a qualitatively way to measure what's your RG approximation error. And here this chi means how many states you are keeping during the RG. And here, this is a scheme proposed by Evans and Vidal. You notice that when you increase the number of couplings you are kept in your RG, the error will decay systematically. And if you check the estimated exponents, and you see also that when you increase the number of couplings, the error will decay systematically. And so these two also kind of propose this method which achieved very successfully 2D real space RG. And we kind of want to push this success to 3D. And what happens if you apply this block tensor transformation in 3D? If you use a two-state approximation, as this is done in this paper, and you will get an error for thermal exponents for about 20%, which is an improvement from Cardinal's original 50%, but it is still very large. And the nice thing about this reformulation is that you can very straightforwardly increase the coupling constant, number of coupling constant. So we perform a thorough analysis and increase the number of states up to 20. And here is its behavior of the RG flow. Notice that the RG flow of the RG error grows very quickly with the RG step. And when you increase the number of couplings, here if you do a 10-state approximation, the error for the first step is relatively small, but it shoots up very quickly to like more than 10% or 20%. And around the critical region, when you keep more states, you even have a larger RG error, which is not very satisfying because you wish that when you keep more coupling constant, you can reduce the error, but this is not very good. And if you just ignore this and do the linearization of RG and get the exponents, here you see that the estimation error for the first two exponents will kind of stabilize when you increase the this bound dimension chi to like 20, and it will stabilize around 10 or 20%, which is again not very satisfying, because here the two-state approximation will only take less than 1 minute in your PC. But if you keep like 20 couplings, you need to use a supercomputer and run for a day, but still you have very similar approximation error. So how to solve this behavior? The key is to again use the original idea of Levin and Nave by thinking about how does the entanglement entropy scales. And in 3D, it scales linearly when you increase the size of the block. And this increase of entropy is kind of in contradiction or inconsistent with the numerical practice of only keeping a constant number of couplings in your RG method. So we have to find a way to filter out boundary entanglement in 3D, TNRG, this tensor block. And so we take the idea from 2D of this entanglement filtering developed by people like Evans and Vidal and Haru and many other people. The idea is that before you are doing this block tensor transformation, you go to its diagonal block and try to filter out all the short range entanglement there. So numerically, people have discovered that this is an efficient way to dealing with the short range entanglement here in 2D. So we kind of generalize this idea to 3D and want to see whether it works well. Here I show again the RG error flow before adding any entanglement filtering and after adding entanglement filtering. And you kind of realize that instead of shooting up very fast to like 10%, if you add this filtering, the RG error will remain for about 3 or 4%. And if you, this kind of indicates that you kind of can approach to the critical fixed point, this tensor. And you do the linearization of this RG, and you find that the first two exponents have much less approximation error. For this one, this energy density, it is like 1%. For spin, it is like 5%. And as a comparison, for the majority of well-developed methods, these two errors range from 1% to 0.01%. So here we are approaching this kind of state-of-art methods. That's all.